Alright, so let's begin, guys. Alright, so the first one, number one, this one talks about a 900 kilogram car traveling east. So let's go ahead and draw a picture of that. So I've got a coordinate system, XY coordinate system. And I've got a car traveling at, so this is mass of 900 kilograms, traveling east at a speed of 15 meters per second. Then I've got a car, another car, that has a mass of 750 kilograms traveling north at 20 meters per second. Okay. And they're on a collision course. They're going to collide at the intersection. Okay. So they'll be at the intersection at the exact same time, and they're going to collide, and then they're going to enmesh. What does that mean when they become enmeshed? That means that they're going to stick together, right, after the collision. So they're going to collide, stick together, and then they're going to move as one body with a final velocity Vf. Okay, that makes an angle theta counterclockwise for the positive x-axis. So what we want to do is we want to calculate what that is. So in what direction does the wreckage move after the collision, and also what is the speed of the wreckage after the collision? And what type of collision is this again? Completely inelastic. Remember, whenever two objects collide and they stick together after the collision, that's going to be a completely inelastic collision. And in completely inelastic collisions, just like any other collision, momentum will be conserved. Energy is not conserved. So do not use conservation of energy to do a problem like this. So first thing, rule of thumb, when you see the exam tomorrow, whenever two objects are colliding, do not use energy in order to do that problem. Okay? Use momentum instead. Okay? So here two objects are colliding. So this is a two-dimensional collision, right? Because I have an x and a y. One's traveling north, the other one's traveling east, right? So I'm going to do momentum conservation, and in order to do momentum conservation in two dimensions, I'm going to have to break up momentum into components, because after all, momentum's a vector, right? So I'm going to do a p initial x, so that's the x component of the initial momentum. So if you look, really just this here is the initial configuration of the system, right? I have a car traveling east, I have a car traveling north. So, does this guy have any x velocity?
Yes.
Yes, that guy has x velocity. So therefore, it will contribute to the x momentum. But now you have to ask yourself, is all of its velocity along the x direction, or is only part of it along the x direction? Does everybody agree that all of it is along the x direction? Because that car is traveling east, so none of it is in the y direction. And that doesn't have a y component in other words. So that means that I'm using the equation P is equal to mv for momentum, right? So the momentum of the car is going to be the mass times the x component of the velocity, which in this case is positive 15. What about this car? Does it have an x component, or is that just solely y direction? It's solely y, so has no x component. So we're done with the x component of the initial. Now, why are we not worrying about the v final? Because that's after the collision. That doesn't come into play when we're talking about initial. So now we do 900 times 15. That's going to give you 13,500. Okay. And what are the units for momentum? Joules, is that true or false? False. That's energy. So this is momentum. This is either Newton second or equivalently a kilogram times a meter per second. Okay, it's the same thing. So I have 13,500 Newton seconds of positive x momentum. Okay. Now, I'm going to do the same thing. I'm still initial. I have not even talked about final yet. Initial, but this time y direction. So let's see. Does this guy have any y velocity or y components of velocity?
No.
This guy here? Nope. But what about this guy? Yes. So that guy is going to be 750. That's the mass. Kilograms times velocity, which is positive because it's up 20 meters per second. So that should give you like 15,000. 15,000 Newton seconds. Okay. All right. So do you see how you start off with a positive y momentum and a positive x momentum? Does everybody see that? Since your final x should be exactly equal to your initial x, and your final y should be exactly equal to your initial y because of momentum conservation, that already tells you that your final x momentum should be greater than 0. Does everybody agree? It should be 13,500. And your final y momentum should be greater than 0. Does everybody agree? In what quadrant is x and y, or x and y both positive?
1.
Quadrant 1. Therefore, this object will be traveling in quadrant number 1. Does everybody see that? That's how we determine it. So take a look. So now we've got our initials. So we have to do finals now. When we do finals, we're now looking here. Okay, that's our final. So first thing you got to do is you got to break up that velocity into its components. So in order to do that, you draw a triangle, right? So we're going to do that. Let me draw that with a blue pen so you can see. I'm going to draw that. So that's your V final X component. That's your V final Y component. Okay. So now your X component, is that adjacent to the theta or is it opposite? That's adjacent, right? So that's going to be VF cosine of theta. Okay. And then the V final Y, that's just going to be V final sine of theta. Because it's opposite. It's across from the theta, so it's going to be sine of theta times VF. Alright, so now that we've got that, we can actually do our P final, but X component. Remember, when we're dealing in 2 dimensions, we have to break up the momentum into its components. Alright, so P final X. So if we look at P final X, how much mass is moving now? So remember, this is the direction that the wreckage takes, right? How much mass is moving now if both cars are together?
The sum of both masses.
The sum of both masses. So in a completely elastic collision, at the end you're going to add the masses because now both of them are moving together as one body. And then since you're dealing with the X momentum, you're now going to use the X component of the velocity. So that's going to be VF cosine of theta. And you're going to do this exact same thing, but this time for the Y component. So still, you have 900 plus 750 kilograms moving, and then times, since it's the Y component of the momentum, times the Y component of the velocity, right? So VF sine of theta. Note that to get this, all I'm doing is using the equation momentum is equal to mass times velocity. Here's the total moving mass in both cases, and here's the Y velocity here, because X velocity here, because I'm doing X momentum. And here's the Y velocity since I'm using Y momentum. Okay. Alright, so now let's rewrite this. So P final X, that's going to be 1650. That's just the sum of these two. VF cosine of theta. And then P final Y is 1650 VF sine of theta. So now I've got these guys. Now, momentum's a vector, right? So first of all, before I move on, I want to make sure everybody understands how we got these. Is everybody comfortable? Okay, so now that we've got that, we know momentum's conserved, right? So that means P initial vector has to equal P final vector. And we know momentum's a vector, right? So we have to say that the initial momentum vector is equal to the final momentum vector. And why is momentum conserved here? Because there will be no unbalanced external forces acting on these cars when they collide. Would you agree with me that they put forces on each other? But those are internal forces. Those are forces that exist within the system. So it does not change the momentum of the system. So here's the thing. What you want to do is you want to remember that in order for 2 vectors to be equivalent, their components must be equivalent. So now what we're going to do is we're going to set like components equal to each other. So X components are going to be equal. So I get 2 scalar equations that come out of this. P initial X equals P final X. That's the first equation that comes out of it. So we're going to have 13,500. That's my initial X, equals my final X, which is 1650 VF cosine of theta. So this is my first equation. And how many variables does that equation have? It has 2. The angle, that's the direction in which the wreckage takes after, and VF, which is the final speed of the wreckage. Okay. Now I also have to set the Y components equal to each other. So P initial Y equals P final Y. So when I do that, I end up with, remember P initial Y was 15,000, so that's going to be 15,000 is equal to, and then my P final Y is 1650 VF sine of theta. So there's my next equation. There it is. So I have these 2 equations. Okay. Does everybody see how we got these 2 equations? Is everybody good? Okay. So now, after this, the physics is done. So at this point, if you see something like this on a test, and you've shown me this, you've racked up most of the credit for the question. Okay, now I'm going to just remind you how you would algebraically solve this. So what you can do is you can take this guy and you can go ahead and solve for VF in terms of theta. So I'm going to divide. So I have 13,500 divided by 1650 times the cosine of theta. Does everybody see how I solve for VF in terms of theta? There. Okay. And the reason for doing this is because now what I can do is I can substitute this VF right in here so that I can eliminate VF from that equation. Okay. So by doing that, I now have 15,000 is equal to 1650 times VF, but VF now, using the first equation, is just 13,500 over 1650 cosine of theta, multiplied by, of course, there's a sine of theta there as well. So you end up with this. Now, what do you notice about this? Something's going to cancel. There will be something with tangent, that's true, but what cancels? The 1650 cancels, right? And I end up having, and remember, sine of theta is the same thing as sine of theta over 1. So I end up having something like sine of theta divided by the cosine of theta. And we know our trig identities, that ends up being just tangent of theta, right? So we end up with 15,000 is equal to 13,500 times the tangent of theta. Now, how many variables do I have in that equation? I just have one variable, that's it. So now I can actually solve that equation for theta. I'm going to be able to solve it. So I'm going to divide. So when I do that, I have 15,000 divided by 13,500 is equal to the tangent of theta. And to solve that equation, what can I do? I can take the arctangent of both sides, right? So let's take the arctangent. So I have theta is equal to the arctangent of 15,000 divided by 13,500. So let's check out what that angle is. It should be about
48 degrees.
48? Okay. So 48 degrees. So that's the direction that the wreckage takes after the collision. And this would be, of course, 48 degrees north of east. So now, how would I get the final speed of the wreckage? Would I have to do this all over again, or is there an easier way? Plug it back in, right? I have a relationship between the final speed of the wreckage and the angle. So all I would have to do now is just substitute theta right there. So that means that your VF, and just know that VF here actually stands for, its shorthand for the magnitude of the final velocity, which is the speed, the final speed of the wreckage, is going to be equal to 13,500 divided by 1650 times the cosine of the angle, which is 48 degrees. So let's plug that in real quick to see what we can get. So we're getting 12.2 meters per second. So that means the final velocity after they collide, okay, the final velocity of the wreckage is going to be VF is equal to 12.2 meters per second, that's the magnitude of the vector, at 48 degrees north of east. That would be the direction of the vector. Okay. So does everybody see how we got this? Is everybody comfortable? Can I clarify any of the steps? Everybody's good?